Good evening, dear students. Today we will be discussing our second session on ellipse, and that is in continuation of um, our previous session, what we discussed in the last class. So today we will start with equation of an ellipse in origin shifted form. Um, If you recall, in the previous class, when we discussed the standard equation of an ellipse, there we discussed the center is at the origin. Correct, dear students? Now, what we are going to discuss that when the origin is not in the, when the center is not at the origin, rather it is at a point, arbitrary point alpha comma beta. Now, before I proceed further, could you please confirm someone that you are able to hear my voice very clearly and able to view the screen properly?
Yes, sir.
Okay, great. Thanks for the confirmation. Okay, so if you recall that, standard equation of an ellipse was what? X square by a square plus y square by b square equal to 1. And different attributes we discussed on ellipse, like, the vertex, the center, not vertex, it is center, foci, directrix, major axis, minor axis, length of major axis, length of minor axis, length of latus rectum, and eccentricity. Now, if we make this equation from x square by a square plus y square by b square equal to 1, and that equation is having the center at the origin. Now, if we shift that origin from, if we shift the center, I repeat that, I repeat, the statement, dear students, x square by a square plus y square by b square equal to 1. If you look into this particular equation, dear students, that x square by a square plus y square by b square equal to 1. This is an equation of an ellipse with center at origin. Now, when we move the center from origin to the point alpha comma beta, I repeat, dear students, when we move the center from origin to the point alpha comma beta, then what will be the equation? So, the equation of an ellipse with its center at alpha comma beta is obtained something like the following. I'm just going to write it here. And the equation is something like this, that x minus alpha whole square plus y minus beta whole square by b square is equal to 1. So, as you see, and that what I wrote in the red color, that x square by a square plus y square by b square equal to 1 is the equation of an ellipse with the center at the point 0, comma 0. If you look into the this ellipse, its center is at the point 0, comma 0. And when you see this equation, x minus alpha whole square plus y minus beta whole square, sorry, x minus alpha whole square by a square plus y minus beta whole square by b square equal to 1. This is an equation where the center is actually at the point alpha comma beta. Now, if we take that x minus alpha equal to capital X, as I wrote here, and y minus beta equal to capital Y, then this equation, what you see, that x minus alpha whole square by a square plus y minus beta whole square by b square equal to 1, it actually transformed to capital X square by a square plus capital Y square by b square equal to 1. Now, if you look into this equation, capital X square by a square plus capital Y square by b square equal to 1, the center of this ellipse is at the point 0, comma 0. And the other attributes can be obtained by replacing x by capital X and y by capital Y. And what is meant by the other attributes, that we discussed in the previous session. You can have a look into the video lecture, what is available in the online platform and also available in the YouTube. So this is about the origin shifted form. Now, dear students, what I'm going to discuss is the next point is that parametric form and auxiliary circle, and that I'm going to discuss into the next slide. So here the point of discussion is that parametric form and auxiliary circle. Now, if you look into this ellipse, not the circle, the elliptic part, this one that I'm talking about, this one, this ellipse. Okay. Now, in that ellipse, we are taking a arbitrary point P. Okay, on that ellipse. Okay, and we define that point with a parameter called theta. So, what is the equation of that ellipse? Equation of the ellipse is that x square by a square plus y square by b square equal to 1. X square by a square plus y square by b square equal to 1. Now, on that ellipse, we are so this is the equation of the ellipse. If I write, so this is the equation of the ellipse: x square by a square plus y square by b square is equal to 1. Now, on that ellipse, we are taking a point theta. Theta is a parameter, and what is the coordinate we are going to take it? We are going to take it the coordinate as a cos theta, comma b sin theta. Okay, where theta is a parameter. Okay, and the value of theta varies from point to point. As you vary theta, then you get different point P on that ellipse. Okay. Now we are going to discuss more about that point theta. So if you look into it, that theta varies from 0 to 2 pi. Correct. So if you look into it, that when the point, if we take the point at A, then theta is 0. Then then after that we varies this one, the point, and we get different values of theta. Now, if you look into this, the equation of the ellipse, that x square by a square plus y square by b square, its parametric form is that x equal to a cos theta and y equal to b sin theta. Now, dear students, if you recall, the significance of parametric form is that if you see the pure equation of the ellipse, pure equation means I wanted to mean the Cartesian coordinate equation. Okay, so equation which is represented in the Cartesian coordinate, that is x square by a square plus y square by b square equal to 1, and you see there are two unknowns, x and y. Correct. Now, if you see that same equation, if we represent by means of parameter, okay, so what we are going to get, x is equal to a cos theta and y is equal to b sin theta. X is equal to a cos theta and y is equal to b sin theta. That is the parametric form of that ellipse. So let me write it down what I just said, dear students. So any point p theta, okay, any point p theta on the ellipse x square by a square plus y square by b square equal to 1 is given by a cos theta comma b sin theta, where theta is a parameter. Okay, any point theta on the ellipse x square by a square plus y square by b square equal to 1 is given by a cos theta comma b sin theta, where theta is a parameter and the value of theta varies from point to point. Here theta, which is varying from 0 to 2 pi, is called the eccentric angle of the point P. Okay, So that we are going to discuss is, okay, that what is that accepting angle, and then from there we are going to discuss a new point, a new concept called auxiliary circle. So if you see, dear students, in that adjoining diagram there is a circle. What is that circle? That circle is known as the auxiliary circle. So an auxiliary circle is happen to an ellipse. So the auxiliary circle of an ellipse is a circle whose center is that of the of the ellipse, that as the ellipse, okay, and diameter equal to the length of the major axis of the ellipse, okay, and the diameter, I repeat, and the diameter equal to the length of the major axis of the ellipse. So what happened is that if you look into this equation, x square by a square plus y square by b square equal to 1, that ellipse where a is greater than b, okay, then the length of the major axis, is 2a. So then what we are going to get it is that, the equation of the corresponding auxiliary circle become x square plus y square equal to a square. Got it, dear students? So what I wanted to mean is this, something like this. The auxiliary circle of an ellipse is a circle whose center is as same as that of the ellipse, okay, and diameter equal to the length of the major axis. What is the length of the major axis of an ellipse, dear students? If you look into, if you remember, length of the major axis is 2a. Why it is 2a? That is what the convention. But how come we know that 2a is the major axis? Because in the equation of the ellipse, we are considering that a is greater than b. As we are considering a is greater than b, so the length of the major axis is 2a. As length of the major axis is 2a, that becomes the diameter of the corresponding auxiliary circle. So then what will be the radius of the auxiliary circle A? So equation of the auxiliary circle will be x square plus y square equal to a square, because origin is the center of the ellipse. So origin should also be the center of the corresponding auxiliary circle. Okay, so whatever we get is that, so if the equation of the ellipse is x square by a square plus y square by b square equal to 1, in which a is greater than b, then we get the equation of the corresponding auxiliary circle as x square plus y square equal to a square. Correct, dear students? Okay. Now, as we have a understanding about that auxiliary circle of an ellipse, so now let's look into the picture, okay, that corresponding diagram. If you see this point P and this point Q, okay, they are actually related. Okay, what is that? If you look into that, the the coordinate of the point P is what? A cos theta b sin theta, okay, and then we get corresponding to this point P on that ellipse, x square by a square plus y square by b square equal to 1, we get a point Q on the auxiliary circle. So that point Q will have a coordinate, that you can find it out, a cos theta, a sin theta. Correct or not? So what I wanted to mean is that if you get the point P, if we get the coordinate of the point P as a cos theta comma b sin theta, then the corresponding point on Q is actually, what we are going to get is that a cos theta comma a sin theta, a cos theta comma a sin theta, and that point Q is on the corresponding auxiliary circle, and the point P is on the ellipse. So corresponding to the point P, a cos theta comma b sin theta on that ellipse x square by a square plus y square by b square equal to 1, we get another point Q with coordinate a cos theta comma a sin theta on the corresponding auxiliary circle, and these are known as the corresponding points. Okay, dear students, so what is corresponding point then? What we learned about the corresponding point is something like this. If P A cos theta comma B sin theta. Let that picture come. Yeah, it came. If P A cos theta comma B sin theta is any point on the ellipse x square by a square plus y square by b square equal to 1, in which a is greater than b, then the point Q a cos theta comma a sin theta on the auxiliary circle corresponding to the point P theta is called the corresponding point. Correct, dear students? So this is known as the corresponding point of that one. Now, here I would like to mention you 2 points, and that is also very important to know about these 2 points, and I'm going to discuss with you on these 2 points. The first point is that, a point P on the ellipse and the corresponding Q on the auxiliary circle, lie on the same side of the major axis. Let that picture, let the portion of that study material come, and it will be more, you'll be able to read it out. So here it is, you can read it out meanwhile. A point P on the ellipse, okay, and the corresponding point Q on the auxiliary circle lie on the same side of the major axis. The line joining the point P and Q always parallel to the minor axis of the ellipse. So these are the 2 fundamental points about an arbitrary point on the ellipse and the corresponding point on the auxiliary circle. Okay, now the next point what we are going to discuss is called the focal distance. The next point what I'm going to discuss is called the focal distance, and that I'm going to discuss in the next slide. So in the term focal distance, the word focal deals that it is something related to the focus. So let's understand what is the focal distance. Okay, let us consider the equation of the ellipse as x square by a square plus y square by b square equal to 1. Okay, and let us take a arbitrary point P on the ellipse, and we know the S is any of the foci. So we know that ellipse has 2 foci. So we are going to take one of these things. So let me let me bring the corresponding diagram so that it will be helpful for us to understand the corresponding discussion. So what you see, dear students, here that correspond, if you look into this diagram, so the focal distance of any point P on the ellipse is is a distance between the point P and any of its focus. There are 2 foci here. One is S and another one is S dash. So we are just considering that distance S. P is any point on that ellipse. So PS is called the focal distance. That means it is the distance between the focus and any point on the ellipse. I repeat, dear students, the focal distance of any point P on the ellipse x square by a square plus y square by b square equal to 1 is the distance between the point P and any of its focus S of the ellipse, that is the distance SP. Now, dear students, okay, there is an important observation. If you look into it, that in the above diagram, if you see, we see that there are 2 focal distances, SP and S dash, SP dash. Okay, and this is a very important observation. I'm going to show you, and this is a very important observation, dear students, and it is, sorry, let me place it here. And here it is. If you go through the statement in this diagram, whatever you see, dear students, that there are 2 focal distances. One is SP and another one is at SP dash. Please note that the following established result: SP plus S dash P is equal to 2A. So this we have given an equation 1. From the above equation 1, we conclude that for any ellipse, the sum of the focal distances of any point on the ellipse is equal to the length of the major axis of the ellipse. Very important observation. So I repeat once more, dear students. For any ellipse, the sum of focal distances of any point on the ellipse is equal to the length of the major axis of the ellipse. So that means there are two foci. So hence there are two focal distances. One is that SP and another one is the S dash P. So if we add up, that is SP plus S dash P, that will be equal to the length of the major axis, which is 2A, which is equal to 2A. Right? And obviously, whenever we consider the equation x square by s square plus y square by b square equal to 1, our presumption is that A is greater than B. Hence, we can conclude the the length of the major axis as 2A. So this is about the the focal distance, and that gives us another important discussion. That gives us that alternate way of looking the definition of an ellipse. So how we can define the alternative definition of an ellipse. So I'm going to discuss on that particular point, dear students. Okay, so it leads to the alternative definition of ellipse. So what is that? That I'm going to tell you. Before that, I'm going to show you a diagram. So please have a look into this diagram. As you see, dear students, in this diagram, let S and S dash be two fixed point and P be a variable point. I repeat, dear students, in this diagram, what you see that S and S dash be two fixed points and P be a variable point which moves in a plane such that SP plus S dash P so SP plus S dash P is equal to what is that? SP plus S dash P is equal to what I wanted to say is that SP plus S dash P is equal to K. What is K? Is a real constant. So let S and S dash be two fixed points and P be a variable point which moves in a plane such that SP plus S dash P is equal to K, where K is a real constant. Let's make this arrangement. Okay, I repeat once more, dear students, so that you can get into perspective. S and S dash, as you see in the diagram, S and S dash are two fixed points. S and S dash there are two fixed points. Here is a point S and another point S dash, the fixed point, and P is the point which is actually moving. But it is moving in a plane in such a manner that if you add SP plus S dash P, that is equal to a constant, that is K. So if K is greater than S dash, okay, so what I'm saying is that from here we can conclude two things. Okay, let me first write down the statement. So if you see that S and S dash are the two fixed point and P is a variable point which moves in a plane such that SP plus S dash P is equal to K, where K is a real constant. Now we conclude the following. What is that? If K is greater than S dash, okay, then the locus of the point P is an ellipse. And if K is equal to S dash, then the locus of the point P is a line segment joining S dash. So this is another alternative way of defining ellipse, especially the first point, that if the value of the K, that is a real constant which is nothing but equal to SP plus S dash P, if that value is greater than S dash, then the locus of the point P is an ellipse, qualified to be an ellipse. And if it is exactly equal to S dash, then the locus of the point P is a line segment joining S is dash, and that is what is actually defining by this, and this is the first one is this one. Correct, dear students? So this is another alternative way of defining an ellipse. Now, dear students, the next point what I'm going to discuss is that the position of a point with respect to an ellipse, and that I'm going to discuss in the next point. The position of a point with respect to an ellipse, and that I'm going to take you to the next slide. So that means what, dear students? That you have been given an equation of an ellipse. That means what? The ellipse equation is something like this. The equation of the ellipse is something like this: x square by a square plus y square by b square equal to 1. And one point is given to you, and that point is P. Suppose the coordinate of the point P be alpha comma beta. Now, dear students, if the exact geometric shape of this ellipse and the position of that point is given to you, then it is very easy to determine whether the point is outside the ellipse, on the ellipse, or inside the ellipse. That you can just by observe and say. But when you do not have such scope, only you have been given the algebraic equation of the ellipse and the coordinate of the point, then how you can determine that whether the point is outside the ellipse, on the ellipse, or inside the ellipse? That actually depends on the value of the expression alpha square by a square plus beta square by b square minus 1. Okay, and that I'm going to show you, dear students, here. Okay. So what I wanted to say is that let x square by a square plus y square by b square equal to 1 be the equation of an ellipse, and let the point P alpha comma beta be any arbitrary point. Now the point P alpha comma beta will be outside the ellipse if alpha square plus a square plus beta square by b square minus 1 is greater than 0. So how we can come to this expression, dear students? As we know that equation of the ellipse is x square by a square plus y square by b square equal to 1. From here we can find x square by a square plus y square by b square minus 1. That expression we are finding. And value of that expression at that particular point alpha comma beta. That means you replace x by alpha and y by beta. Then what is the value of the expression we are getting? Alpha square by a square plus beta square by b square minus 1. Now, if that value is greater than 0, then you can conclude the point alpha comma beta is outside of the ellipse. If we get the value of alpha square by a square plus beta square by b square minus 1 equal to 0, then you can say the point alpha beta is on the ellipse. And if we get alpha square by a square plus beta square by b square minus 1 is less than 0, then you can say the point alpha comma beta is inside the ellipse. So this is the way we can determine whether the point, a point whose coordinate is given, is outside the ellipse, on the ellipse, or inside the ellipse. Correct, dear students? Now, the next point what I'm going to discuss, dear students, is actually the tangent of ellipse. The next point what I'm going to discuss is the tangents of ellipse. I hope all of you have a very clear idea about what is known by tangent. We have discussed, several times. It is a straight line which touches a curve. In this case, the curve of discussion is ellipse. And let's see how we can find the equation of the tangent of ellipse. Okay, and in all these cases, dear students, as you have observed that we are going to take the equation of an ellipse in the standard form, that is x square by a square plus y square by b square equal to 1. Now, if you look into this, dear students, that if let x square by a square plus y square by b square equal to 1 be the equation of an ellipse. Now, the equation of the tangent. Now, the equation of the tangent to the ellipse at any arbitrary point x1, y1, which is having the Cartesian coordinate of that point P become x1, y1 is nothing but x1 by a square plus y1 by b square equal to 1. That is the equation of the tangent to the ellipse at any arbitrary point P x1, y1. And if the point P is an parametric point, that is theta, that is a cos theta comma b sin theta, then the equation of the tangent is turning out to be x cos theta by a plus y sin theta by b equal to 1. That is in any parametric point theta. So these are the two important things, because so far, dear students, we have learned about two points, two different type of points on an ellipse. That is, one is the Cartesian coordinate, that is which is quite general, x1, y1, having both x coordinate and y coordinate, and another form that is coordinate in the parametric form, that is a cos theta comma b sin theta, in which we have only one parameter, that is theta. That is one unknown in that way also you can say. So now if we have that ellipse in which we are going to draw the tangent on a parametric point theta, then the equation of the tangent will be x cos theta by a plus y sin theta by b equal to 1. I hope these 2 points are clear. Now, the general equation of tangent is y equal to mx plus minus a square plus minus, y equal to mx plus minus square root of a square m square plus b square, where m is a real number. Here it is to be noted that for the same slope m, it is possible to have two tangents of the ellipse. You can observe this thing. For any slope, you can always find two tangents. Okay, one on the upper half of the ellipse and one on the lower half of the ellipse. Let me show you by means of a diagram, dear students, so that it will be very clear to you. Okay, so for that I need to take the image of an ellipse. So let me take it, and then after that I will explain you. Okay, so let me take the ellipse from here itself. So dear students, if you look into this ellipse, and if we assume that equation of this ellipse is x square by a square plus y square by b square equal to 1, and let's take a point here that at this point we are drawing a tangent. So if we draw a tangent, so tangent it will be something like this. Correct, dear students? Now, parallel to this line, you can find another line which is also a tangent to that same ellipse, but in the lower half. So if I draw the tangent in the blue color, so it will be something like this. If you see the blue line and the green line, they are actually parallel to each other, and we are having two tangents, and that is why both these tangents is having the same slope, and hence we consider the slope as m. So dear students, what we are discussing is that the general equation of the tangent is y equal to mx plus minus square root of a square m square plus b square, where m belongs to r. Here it is to be noted that for the same slope m, it is possible to have two tangents to the ellipse, one in the upper half, as you see here, and one in the lower half of the ellipse. Correct, dear students? This is all about the equation of a tangent to an ellipse. Correct? Now, dear students, the next point, what I'm going to discuss with you is about the director circle of an ellipse. So, a lot of points I'm discussing, dear students, and once our theory discussion is done, then we'll start solving numerical questions as well. Okay. So the next point what I'm going to discuss is the director circle of ellipse, and it is the point of our discussion. So what is that, dear students? So let me first take the diagram first. Okay, let me show you the diagram, and based on that diagram I can explain you I can explain you further. Please just concentrate on, from this diagram, just concentrate on the ellipse, which is that this one. And what is the equation of that ellipse? Equation of that ellipse is that x square by a square plus y square by b square equal to 1. Now, very importantly, note it down, dear students. Let us take a point P such that two mutually perpendicular tangents can be drawn to an ellipse from that point P. So we are taking a point P here, dear students. From that P, you see there are two tangents has been drawn. One is PT1 and say the other one is that PT2. Such that from any external point, you can always draw two tangents to an ellipse. Okay, like circle. From an external point, you can draw two tangents to a circle. No? Similarly, from an external point, you can draw two tangents to an ellipse, as you see in that adjoining diagram, PT1 and PT2. But dear students, here we are interested in such two tangents so that their angle between them is 90 degree. As you see here, this angle is 90 degree, right angle. So I repeat once more. Let us take a point P such that two mutually perpendicular tangents can be drawn to an ellipse from this point P. Now, the locus of such points is actually describe a circle, and that circle is known as director circle. Suppose, here is a point P. After some time, you get another point. So from this point also, you can draw two tangents, and you will find the angle between those two tangents is actually 90 degree. Okay, and after some time you can get it here, you get it here like this. Okay, you will get many points, so that from all those points, if you draw two tangents, the angle between those two tangents are 90 degree, or in other words, we can say those two tangents are perpendicular to each other. For example, in this adjoining diagram, we see PT1 and PT2 are perpendicular to each other. Now, the locus of this point P is describe a circle, and that circle is known as the director circle. And dear students, now I'll tell you, now I'll suggest you please concentrate on the entire picture. Okay, so first let me explain you what is meant by this director circle. Okay, let the portion of that material come, and then let me read it out. For that ellipse x square by a square plus y square by b square equal to 1, let us take a point P such that two mutually perpendicular tangents can be drawn to an ellipse from this point P. The locus of that point P is a circle, and that is known as the director circle. So what we can say the other way? So we can say that the director circle of an ellipse is the locus of the point of intersection of any two mutually perpendicular tangents to the ellipse, correct or not? Okay. So the other way, what we can say, and just I'm going to place that statement in front of you, is something like this, that we can say that, dear students, is this statement. We can say that the director circle of an ellipse, I repeat the statement, the director circle of an ellipse is the locus of the point of intersection of any two mutually perpendicular tangents to the ellipse. Correct? Now, let us concentrate on finding the equation of the director circle. So let us now derive the equation of the director circle corresponding to the ellipse x square by a square plus y square by b square equal to 1. Okay, so how we are going to derive it, let's see it, and you will find it very interesting and very straightforward as well. So as the equation of the ellipse is x square by a square plus y square by b square equal to 1, now if we take any arbitrary point, let us take an arbitrary point alpha comma beta outside that ellipse. Now from that outside alpha comma beta, so what I was telling is something like this, is that let me draw an ellipse here. So suppose this is an ellipse. Okay, dear students. Now let us consider a point P here. Okay, arbitrary point having coordinate alpha comma beta. Now, dear students, as we just learned few minutes back, that from that point P, we can draw two tangents, correct or not? So in fact, we can draw the tangent. So let me draw one tangent in the green color. This is one tangent, and another tangent I draw in the blue color. So this is another tangent. Okay, dear students, so you see that one tangent, so it is not exactly looks like a tangent. Yeah, so you see, dear students, so there are two tangents here I have drawn. So one tangent I can say it is PT1, and the other tangents PT1, and here the other tangents PT2. Now, what is the generic equation of this tangent? The generic equation of this tangent, if you remember, it is y equal to mx. Let me write it from the study material so that so let two mutually perpendicular tangents are drawn from an external point alpha comma beta to the ellipse x square by a square plus y square by b square equal to 1. We are going to find the locus of the point alpha beta. Now, out of these two mutually perpendicular tangents, let one of the equation of the tangent be y equal to mx plus square root of a square ms square plus b square. Okay, that we have learned when we discuss about the tangents to an ellipse. Now, if the other tangent is perpendicular to this particular tangent, then that tangent should have a slope minus 1 by m. Quite obvious, correct or not? So it is quite obvious from a the condition of perpendicular of two straight lines. So what I'm saying, dear students, is that then the equation of the other tangent perpendicular to the tangent which is described in the equation 1 will be something like this. Instead of m, we are going to write minus 1 by m. And then what will be the generic equation? The generic equation of the tangent having slope minus 1 by m from an external point alpha comma beta, that is also not required, external point. In this case, external point is out of context. That general equation of a tangent to an ellipse having slope minus 1 by m should be something like this: y equal to minus 1 by m into x plus square root of a square by minus m whole square plus b square. How we observe it? Because we know the general equation of a tangent having slope m to an ellipse x square by a square plus y square by b square equal to 1 is something like y equal to mx plus minus square root of a square m square plus b square. So we just eradicate negative 1, we just take only 1, that is y equal to mx plus square root of a square m square plus b square. So now the other tangent, if it is going to be the perpendicular to the previous one, what I just wrote and is there in the equation 1, has to have a slope of minus 1 by m, dear students. So now, so that means we see that we are going to find the equation of a tangent to an ellipse having slope minus 1 by m. So what we are going to go do it? What we are going to get it? We are going to get it something like this: y is equal to minus 1 by m into x plus square root of a square by minus m whole square plus b square. So from here what we get is that my minus x, my equal to minus x plus square root of a square plus b square m square. That is equation number 2, dear students. Correct? Now, what we are going to do is that we are going to derive. Now, what we are going to find? Alpha beta. Definitely, dear students, alpha beta is the point of intersection of these two straight lines 1 and 2. So that means what? That alpha beta must satisfy both the equations. Correct or not? Alpha beta will satisfy both the equations, and eventually we are going to derive this thing. So I'm going to show you this. Let me place the derivation first, and after that I will explain you in details. So dear students, here it is. If you look into it, the point alpha comma beta lies in both the above straight line 1 and 2, as you see. So definitely this is, easily we can write, because alpha beta is satisfied by both the equations. And from there we made a derivation. We find beta minus m alpha, m beta plus alpha, and then we take a square of both the sides of these two expressions and add it up. And then we get this one. These are all, easily understandable, okay? And then finally, we get that 1 plus m square, we can, into alpha square plus 1 plus m square into beta square is equal to 1 plus m square into a square plus b square. Now 1 plus m square cannot be equal to 0, right? Despite m being any number, any real number, 1 plus m square is always greater than 0, in fact, so not equal to 0. So we get alpha square plus beta square equal to a square plus b square. Now, dear students, if you recall our locus study, how to find the locus of the point alpha comma beta is nothing but replace alpha by x and beta by y. So we get the locus of the point alpha comma beta as x square plus y square is equal to a square plus b square. So dear students, so what we get, the locus of the point alpha comma beta as x square by x square plus y square is equal to a square plus b square. Correct? So we derive that if the equation of the ellipse be x square by a square plus y square by b square equal to 1, then the equation of the corresponding director circle is x square plus y square equal to a square plus b square. So let me write it down what I just said, dear students. So we derive that sorry. So we derive that if the equation of the ellipse be x square by a square plus y square by b square equal to 1, then we derive that if the equation of the ellipse be x square by a square plus y square by b square equal to 1, then the equation of the corresponding director circle is x square plus y square is equal to a square plus b square. So now, dear students, if I take back you to the corresponding diagram, so if you look into this particular ellipse, this particular ellipse equation, if we take as x square by a square plus y square by b square is equal to 1, then the corresponding director circle, this is the director circle, its equation will be x square plus y square is equal to a square plus b square. Okay, remember this thing always, dear students. Okay, now with respect to this, I'm going to tell you two important points. Okay, and with this we'll be concluding discussion on director circle. And what are the two important points? So there I am going to write it down here and followed by its explanation. So the point is that please note the following points. The first point, what I'm saying is that from any point on the director circle, if any two tangents are drawn to the ellipse, then the angle between the tangents must be 90 degrees. That is quite following from the definition of the director circle, because director circle is made by the locus of that point, such points, so that if you draw two tangents from that point to the corresponding ellipse, then the angle between those two tangents become 90 degrees. So hence, obviously, the statement it makes sense that from any point on the director circle, if any two tangents are drawn to the ellipse, the corresponding ellipse, okay, then the angle between those two tangents must be 90 degrees. And the second point is that the director circle of the circle x square plus y square equal to a square is x square plus y square equal to a square. How we get it? So we know that if equation of an ellipse is x square by a square plus y square by b square equal to 1, then what is its director circle? Its director circle is x square plus y square is equal to a square plus b square. Now, if we have x square plus y square equal to a square, So what we get, dear students, x square plus y square equal to a square. That means that x square by a square plus y square by a square equal to 1. So then from here what we can get the corresponding director circle. It should be x square plus y square is equal to a square plus a square, because in this case b become a, and which is nothing but x square plus y square is equal to 2a square. Correct, dear students? So this is all about the director circle of an ellipse. So with this, I would like to conclude the class for today here, dear students. In the next class, we are going to discuss the normal of ellipse, then chord joining 2 points of an ellipse, followed by pair of tangents from an external point, followed by chord of contact, followed by chord of contact in terms of the middle point, and we will conclude our basic discussion on ellipse, and we'll move to solve some problems. Together we will start solving problems. So dear students, with this note, I would like to conclude the class here, unless you have any specific question for me. Thank you very much.